Alright, time for another DraftPhysics.com video presentation. Debatephysics.com also. But again, the debate is just not on the subject, frankly, most of the time. So the Dispar character has made a couple more videos analyzing this, bang a light thing into a heavy thing and create free momentum. And he claims there's some reality to some notion that energy, quote unquote, is a scalar. That is, it doesn't have a direction, even though everything we know that has energy has a direction. And somehow speed or whatever, well, speed doesn't have a direction either. Somehow you're going 60 miles an hour in no direction when you have a speed. Okay, but when you have a velocity, the velocity does have a direction. And that somehow you can subtract directions. So we'll go over these arguments again. Again, he won't touch the actual arguments. He won't explain the disconnect in the evidence. Nothing. And, he just keeps doing his little one-track mind thing where I've made my argument. Okay, the fact is these experiments can be fudged. And I've played the Professor Lewin video over and over. And I'll show it one more time. But anyway... and we're waiting on physicist Michael. So the truth is, the guy has promised that he was going to do this pendulum thing, really show us the free momentum experiment in the simplest, cleanest way possible, using just pendulums. And so far, nothing. Months later, so, you're going to have to talk him into it, people, apparently. At least find out one way or the other. Is he going to do it or isn't he? Frankly, provide us with this certain proof. If it's a real phenomenon, then show us. What's the big deal? All right. So, oh boy, I got a lot of crap here. I gotta get rid of. I got way too many open browser windows. Very dangerous. Anyway, so this is the Professor Lewin. So he did 2 experiments. Now another thing, Dispar shows a video where they're just doing it one way, right? They either do it where the 2 carts stick to each other and move off, or they do it with, a 1-mass cart and a 3-mass cart, and they do the experiment where they bounce off of each other, and they don't ever reverse it. So they just never pick up the carts and just redo it with the heavy thing hitting the light thing and the light thing hitting the heavy thing with the same apparatus, where it's completely possible to do it, but they don't do it. So why don't they do that? Why in all the videos there's not a single case that I know of where they simply just say, okay, we did it this way, let's reverse it and have the heavy thing hit the light thing? How come? Maybe that's more evidence that all these experiments are engineered to produce results. So, I've explained how these carts don't have any similarity to the other carts. Okay, so we could probably move back to a better frame where you can see the 2 carts next to each other. Probably can do that there. It's close. That's a good image, just because you can see clearly there's a weight on the heavier cart and the lighter cart, no such weight.
And now we get one.
Just a minute. Alright, back. Alright, so in this image you can see both carts. You can see that the little cart doesn't have any weight on it. Now obviously when he did the experiment earlier in the same lecture, the little cart does have the weights on it. It doesn't make much sense. There can be twice the, half the weight, or half the weight under that circumstance. And you can also see the little gray putty. It's a a flat piece of putty that he has on the 1-mass carts in this case. And that's obviously what was smushed up and, on the other cart. So, we can just play this through, but there's no, what's the explanation? It is an elastic. It fits the math. This is technically an elastic collision because they don't stick to each other. They do bounce. And all the momentum is conserved. Therefore, you can't really start talking about how a bunch of energy was lost somewhere. So, it just doesn't make any physical sense. How come that doesn't work? Oh, it's always something with these computers. There we go. So you can see the contact is so brief. They bang into each other. The Velcro doesn't work. It doesn't stick. It elastically bounces. And you end up with less than half the velocity. So nowhere close to 2/3 the velocity, right? It's less than half the velocity. So Disbar analyze that experiment. Explain, where did all the energy go? And then show the other experiment. Explain how you can explain how there's this huge difference in how the weights are configured on these carts. Even though it's supposed to be 2-to-1, why the big huge difference in the features on the carts? All right. So that we don't hear. All right. So let's just go through, all these. The argument's relevant. I mean, there are like 4 arguments that are pretty solid that they just never touch, they never explain, they don't do a damn thing. So the experiment that physicist Michael is supposed to be doing, that'll prove it one way or the other. All right, you take a 1 mass and you plow it into a 3 mass. Just make that clear, I guess. We'll put the little 3s on here. And you have a certain amount of momentum going, then when you collide the light thing with the heavy thing, somehow you get 2/3 of the velocity continues to go this way, and 1/3 goes this way, and you end up with this 150 momentums. So you increase the amount of momentum in the experiment. Just no doubt about it. You have more going that way. All right, so you've created more force in a direction. So if you were hammering a nail, obviously, if somebody said, well, I can hammer with 100 momentums or I can hammer with 150 momentum, I can reconfigure the hammer. You're going to, if you want the nail to go in, you get $1 million if the nail actually penetrates the wood. You're going to vote for the 150. It's real energy. Momentum is real energy. It can do real work. And you have more of it going this way. Yeah, you have some going back this way, but who cares? Really not interesting. But what is interesting is they say the total momentum of this system, that is the total amount of masses moving velocities, is now 200. And then when this 200, because of gravity, comes back again, their theory is that somehow half the momentum disappears. And it does disappear. There's no evidence that these things get hot, that there's any pieces flying off. No evidence where the momentum disappears to, and only the 100 pops back out again. You're back where you started. So the system will oscillate, and it will create free momentum, extra momentum, and then less momentum, and extra momentum, and less, it'll give it, and then it'll take it away, and it'll give it, and they'll take it away. So they're actually saying that if you have a car crash between something that has 150 momentums and something that has 50, with these kind of mass ratios, that somehow what will pop out of the crash is only 100. Elastic cars. All right, so it doesn't make any sense on its face. It certainly does disagree with any notion that you have to conserve momentum. So they can't really keep arguing that conserving momentum means something in their physics when clearly they say you really don't have to. All right, and so this just relates to the other version of this. They're all just versions of the same thing, but their claim that you take a rubber ball and you throw it at a wall with a certain momentum, and what's going to happen is that I should use the 2 colors just for emphasis. Their argument is that the immovable wall, if the wall doesn't yield, doesn't roll, doesn't go anywhere, is that 200 momentums goes into the wall, and that you get 100 back this way. Because their theory is that the 100 subtracted over the 200 leaves you with 100 going that way, which is it's obviously a reflection, frankly, from my point of view. In my entire life, experiencing throwing things, you can imagine I threw a few things in my life. I never saw this take place. What I saw take place is that if I make this a little bit more yieldy, that is, it can roll this time, and it will move, that the more this moves, the less this bounces back. That's my experience with reality. And that if this moves with all the momentum. That is, if I can get this to have 100 momentum in it and rolling with 100 momentum, I'm not going to get anything back. The ball's just going to fall down, straight down the end. It's all finished playing. So it doesn't make any sense. You know, the more the ball bounces back, the more energy that went into the wall. When, no, all my personal experience says the more the wall moves, the less the ball bounces back, clearly indicating that I'm not going to be putting all this extra energy into anything. All right. So that's pretty clear evidence. It doesn't work. It doesn't work like that. So that relates to, you know, the other thing they won't talk about is the anvil. You know, I can make an unheat treated anvil, okay, regular steel, and you know, it just sort of points out how all of these experiments, you just have to, you know, you change them just a little bit and it makes a huge difference. So I could drop a ball, it'll have a certain momentum, 100, and the fact is that the steel will dent a little bit. Okay, unheat treated steel isn't all as hard as we'd like it to believe it is. And the fact is the ball will dent, and you can actually see the dents that it'll make. Okay, and so you'll get less back, and you get maybe 6 bounces. But if you heat treat the anvil, you have really hard steel, and you polish it well, it can bounce 200 times. So yeah, it loses a little eventually. Okay, so these bounces are very small. But the fact is it does a lot of bouncing. And their theory is every single time the ball hits, okay, it's putting twice the momentum into the anvil. It's moving the earth. So it's like 200 plus 999 and then plus 193 and then plus 187 and then plus. You know, a huge amount of energy somehow is going into the anvil. And I only dropped it with 200. I mean, with, you know, 100 momentum, let's say. That's all that went in. Now, that makes sense to you? That I can put, say, 1,500. Okay, I can put 100 in, and I can make 1,500 of energy out. That makes sense to you? Or is the more sensible conclusion that the energy was resisted? It didn't get through the anvil. It didn't go anywhere. It's a big, heavy thing. It didn't move at all, and it simply reflected the energy. And what you got back is just a reflection. You got back what you put in because it rejected it. It didn't absorb it. All right. I mean, you could relate this to photons, you know. I mean, can you both reflect the photon and absorb the photon? Is that possible? I mean, you know, you could heat the substance and also reflect. No, I think you understand that the energy don't work that way. All right, so this relates again to the 5 mass object, you know, going 10 velocity. All right, I add another 5. All right, I end up with a 10. Okay, a 10 mass. All right, going half the velocity, 5 velocity. All right. Simply stated, it makes perfectly good sense. Momentum is perfectly conserved. No problems. Universe works. Their MV squared says that somehow, whatever they think energy is, that somehow I lost half the energy here. So I just want them to explain how I could lose half the energy. That is, something dramatic happened when I added this extra mass. You know, let's say I just poured it into a bucket here. This was a bucket, and I just filled it with 5 masses, 5 kilograms of more fluid, or something like that. You know, really thick fluid, so it didn't slosh around. Where are you going to say the extra energy? Where'd it go? So you lost 1/2 the KE. 1/2 the kinetic energy will be gone, disappears. It's not in your product. And what's your explanation? Because if you're going to say, well, I knocked a piece off and it went out here, well, then I'm going to say, well, you can't put, you know, let's say 100 momentums in. You got 100 out here. You can't have 5 going over here. Okay. Can't do that. You can't have more motion than you started with, mass moving. So again, Professor Lewin says nature can deal with kinetic energy one way or the other, but nature can't finagle momentum. Is he right or is he wrong? All right, and then I guess I'll just end with the ballistic pendulum, another example where they don't explain anything. So the bullet goes in, okay, and let's just say it has 2,000 joules for the fun of it. And obviously I would say it has a certain amount of momentum. So let's just say it has 150 of momentum, MV. All right. And what's going to happen is, well, the bullet's going to go into the ballistic pendulum, and yes, it's going to push some clay this way. It's going to do some of that. All right. It's going to cause some motion in the clay and some heating of the clay. But what it's primarily going to do is dissipate the motion in this direction. Okay. So it's going to basically exchange its momentum with this big heavy pendulum. So this is a gigantic heavy mass. All right, it's going to move the heavy mass at a very low velocity. So the velocity is going to be really low. All right, and the velocity here was very high. All right, so we're going to start with a little m and a big giant V, and we're going to end up with a big V and a little m, and we're only going to lose a little tiny bit. So we'll conserve 98% of the momentum. We'll lose a little bit. Some of the energy is going to get lost as heat and things going the wrong way. You know, pieces of clay moving around. And that'll eventually end with heat. The clay moves, and when the clay stops, that's heat. It lost its motion to heating the clay. So the motion of the clay will be eventually seen as infrared radiation or some form of heat. All right, so we've done our job as physicists. We've conserved the motion in the universe, the energy. Everything's just fine. And again, what does kinetic energy do to this simple diagram? It makes an insane mess out of it, right? Because it basically says I went in with 2,000 joules of energy, 2,000 joules, and I'm going to end up with 2 or less. Less than, I'm going to lose 99.94 in Professor Lewin's analysis. 99.94 of the momentum, percent of the momentum gone. I mean the kinetic energy gone, disappeared. So where did it go? Where's the explanation? I've got 98% of the momentum. So again, are you going to make arguments that there's 2,000 joules worth of heat inside of this clay, and that somehow I made those 2,000 joules of heat with only 2% of the momentum? I only used up 2% of the momentum, and I made 2,000 joules of heat? So that's rational to you people? That makes sense to you. You can say, yes, that makes perfectly good sense. I can't say it. I can't. There's no way it makes any sense at all. It's clear the kinetic energy theory is just a nuisance. It just gets in the way. Again, there's no evidence that kinetic energy theory has produced a single thing ever that was useful. It hasn't made airplanes fly, hasn't made motors more efficient, hasn't made turbines more efficient, hasn't done a damn thing ever in the history of mankind. And the only thing the silly formula is used for is to create quarks and gluons and muons and taus. All the accelerator crap is what this stupid formula creates. Wrong answers to questions like how much does an electron weigh? Well, they get the wrong answer because they're using this idiotic formula instead of this momentum formula. So again, we can go right back to the simplest argument. Does NASA, okay, there's a yes and no answer to this question. When NASA is figuring out how to navigate a spaceship, what does it use? I mean, it can't use both formulas, okay? It really can't. It has to use one or the other. Okay, and isn't that sort of just the giveaway? That whatever one it's using is the real one, and the other one is just a nonsense that we're just wasting our time talking about. So what does it think matters? The kinetic energy. So on one side of the ship, I'm going to throw a heavy thing, okay, going slow. All right, so I'm going to have 2 joules of energy. but I'm going to have the same momentums on both sides. Okay. So, and I have the bullet on the other side, 2,000 joules. Oh, so I could just do the gun thing again, you know, the zip gun example. But anyway, this is the space example. So one side of the ship, I throw out the gun, going slow. So it's 1,000 times more mass. Okay, 1,000 times the mass, going 1/1000th of the velocity. All right. So again, we're back to big M and a little v. And then we have on the other side 1,000th of the mass. So we have 1/1000th of the mass going, you know, it should be twice as fast, but it doesn't matter. Well, we'll leave the 2's just for the hell of it. Going 2,000 miles an hour, okay, which is 1,000 times the velocity. This velocity was only 2, okay, 2v, and this one it's 2,000 v. All right, so again, it's just the same thing, right? We got a big V and a little m, and a big M and a little v, and that works. And I say NASA, that's exactly how NASA landed the lunar module on the moon, was to measure the momentum of the gases that it used as exhausts. You know, it shot gases, okay, to, you know, little molecules of matter out of the device, out of little thrusters, and that's how it navigated, okay, that's how it turned, that's how it created thrust, and anti-thrust was to use thrust, and it was measuring it based on how many pounds of pressure it created, what its weight was, its mv, and it didn't bother with 1/2 mv squared at all. And the fact is in this simple example, okay, physicist Michael at least conceded that the spaceship doesn't turn. So even though I only put 2 joules out this side, 2 joules of Ke out this side of the ship, and I put 2,000 joules of Ke out this side, somehow the ship doesn't turn. And if it doesn't turn matter, if it doesn't make matter move, then why are we arguing, right? Because we know it is the same momentum coming out both sides, and it does exactly what you would think the momentum dictates. So clearly, Ke is just made up. It's a fable. The history proves it. Okay, again, does this spar think, okay, that 4 pounds dropped 1 foot is the same impact energy as 1 pound dropped 4 feet? I mean, does he believe it? And does he have any pause or doubt based on the fact that his physics, the physics he's defending, has never done the experiment? They never bothered. They never bothered to do any of these simple experiments. You know, you drop something, you put something on a scale, and it compresses the scale a certain amount, and then you just turn the scale, right? You lock it in that position, put a little lock on the scale. So now it's locked, and you have the object there, and then you can just let it go in space, or, you know, on a very frictionless surface, and see how much velocity it creates. And that'll tell you how much momentum it had just sitting on the scale. But it in fact is pushing into the earth with a pressure. And you've stored the pressure, and then you release the pressure, and it turns out, I would argue, that no matter what I put on the scale, an elephant, and I turn it sideways, it'll move the elephant 1 mile an hour. And if I put a mouse on the scale, and I turn the scale, it'll move the mouse 1 mile an hour. Because that's the actual momentum you have in gravity. But, you know, we won't hear a counter argument to how that theory is nonsense or how that's provably wrong. What experiment proves that not to be true? They don't have any experiments. Nothing. They talk about data, but they don't really create any. So anyway, none of those arguments would be dealt with these slimy, conniving, game-playing jerk. So anyway, enough of a video. So we've been over it and over it, but I'm just saying they haven't made any counter-argument. I mean, I like to present their counter-argument to any one of these statements, but they won't provide the counter-argument. There's no counter-argument provided to any of these examples. No explanation for the complete contradiction of either creating free energy in the form of free momentum or destroying kinetic energy without any evidence that you actually did any of that. Again, they haven't even taken a rolling ball, and rolled it across the surface and actually measured how much impact force it puts on the ground and how much energy it loses to the ground at what rate. They've never even done those experiments. Nothing. They just claim a truth. They don't demonstrate it or prove it in any way. It's just a religion. The Leibnizian religion with the New Testament of Descartes. Yeah. The Old Testament is Leibniz, the New Testament is Descartes. And it's all just a silly, stupid pile of babble. Made up nonsense. All right, enough said.